Ladies and gentlemen, welcome to the Big Bear Math Channel. And as we rev up for the AP Calculus exam, I've got a BC only question for you today. We're taking a look at 2019 free response question number 2, and the theme today is polar functions. And we're going to see an extremely challenging question today, but I hope as we work together here, we're going to put a few new thoughts into your head to help you sort this out. And at the end of the day, you look back and say, you know what, this problem really wasn't as maybe overwhelming as I thought it was initially. Now, the national average on last year's exam for this particular question was a 2.6. That's out of a 9 possible points that the students could earn. The national average was a 2.6, so that tells you just how challenging this question is. But again, let's go ahead and dive in and tackle this bear together. So we were given a picture of a function as well as its corresponding equation, which is always very, very nice. So what they've graphed for us is this r of theta equals 3 radical theta sine of theta squared function. And this question is calculator active. So if you wanted to graph it yourself, you certainly could. You could change your assuming if you are using a TI-84 or an Inspire, you're switching your mode from function mode to polar mode, and you can come up with this graph. They've also given us a window, so to speak, and this could, if you were graphing it, this would be your x min, this would be your x max, and you'd get the same looking picture. So in other words, we're saying when theta equals 0, the value of r is also 0. So we're starting right here at the origin. And as theta increases, we're moving along the curve in this kind of counterclockwise fashion. And we're just slowly making our way around the curve, around the curve, around the curve. Let's see. This particular point right here would be when theta equals pi over 2. We'd continue past there, and eventually theta would equal radical pi, which brings us back to the origin. So we want to find the area of this region S. And if you remember anything about the area of a polar region, what we are is we're kind of sweeping in a counterclockwise motion. We have these small sectors or radial lines that are rotating and rotating. And so let's go ahead and set up our area formula. Now, in general terms, the area is going to be 1/2 the integral from, we could say, I like to say alpha to beta, or you could say theta sub 1 to theta sub 2 of this function r of theta squared d theta. So for our particular problem, the area of region S is just going to be 1/2 the integral from 0 to radical pi. We've got that function 3 radical theta times sine of theta squared, all squared. Plug that into your calculator. I've got my calculator handy here. I got 3.534 for my answer. That's the area of S. Kind of a tough number to get a ballpark idea of, like to see, like, is that really reasonable? Maybe you're expecting the answer to be bigger. And what we don't have is, we don't really have, like, I don't know this Y value, I don't know this X value, so I really don't know how big that region is. But what you could do with your calculator, and I'm going to switch over here to this polar mode, is if you, I'm going to kind of try to put, I'm going to roughly try to put a rectangle around this bear. Oh, geez, that's not good. But what it's going to do is it's going to kind of tell you that the rectangle that may enclose this is approximately, and again, we're just ballparking here, about 1.5. The height is approximately maybe 3.5-ish. And if you multiply those two together, you'd get an answer a little bit bigger than 5, and that's the area of that entire blue rectangle. And so then region S itself is certainly smaller than 5. So going back here, the 3.534 seems a lot more reasonable now all of a sudden. Let's take a look. Let's see if we can slide into part B. And we may go back to that picture they gave us here in just a second. So they said, hey, what is the average distance from the origin to a point on that polar curve? So right away, I see average. So the first thing that popped into my head there was going to be 1 over b minus a integral from a to b of f of x. So this is kind of a formula, so to speak, to find the average value of function f itself. So this would give you the average value of some function f of x. Now, in this case, we want the average distance. Well, I don't know, like, how do I, do I have a formula for distance or whatever? But it's actually way easier than you're thinking. Let's go back up to this picture. I'm going to pick just a random point on this curve. Okay, let's pick this point right here. So there's a theta that corresponds to this point, And when I input that theta into this function right here, it gives me an output of r. And that r, by its very nature, is the distance from this point on the curve to the origin. So by its very definition, r is distance. And now we're trying to find the average distance. So you're really, in a nutshell, trying to find the average value of r itself. That's really all it is. So we could say, let's go 1 over radical pi minus 0, integral from 0 to radical pi. And then we want to find the average of r. I know it seems like it had to be more complicated than that, but that's really all they're asking you to do. And again, grab your calculator, plug that in, and you're going to get 1.580 as the average value of r. And again, I think that seems really reasonable when I consider the graph, and especially remember how we took a look at Desmos and we got to look at how big that curve was. This seems like a very reasonable answer. All right. Now, those two parts were challenging in and of themselves, but we're going to take a huge jump up in difficulty, I think, in my opinion, as we tackle C and D. And they said there's going to be a line that goes through the origin that has a positive slope of m. And that line divides region S into two regions with equal areas. So let's see if we can go into our Desmos picture. Now, just to give you an idea of what the line, I'm going to draw a line at theta equals pi over 3. Okay. Now, I think right out of the gates, you're thinking, okay, that's definitely not the right answer because that did not divide this so-called petal into two congruent regions. But what we're thinking is, let's just label this theta equals pi over 3. This is a unique equation because it's not like in the form of r equals, it's just in the form of theta equals some constant number like that. And let's see if I can make a better estimate. Let's see, maybe this line right here, if I can draw it somewhat straight. So we're thinking this area on this side of the petal is going to be congruent to this area on this other side of the petal. Okay. And let's say that this magical intersection is at theta equals, so it's not pi over 3. I don't really know what it is. I'm just going to call it alpha for right now. So what I'm thinking is the integral from 0 to alpha of r squared d theta is equal to 1/2 the integral from alpha to where? Radical pi of r squared d theta. And so I want to try to find the slope of that line. Let's see if I can come up with a little different color here. Do yellow. I've got to find the slope of this line right here. That's my challenge. All right. Now, what you'll know, if you remember, you're probably the first day you ever took notes on a polar function, is we said, okay, let's draw a line straight down from that point and a line straight over. So the height of that triangle is going to be your y coordinate. The base is going to be your x coordinate. And this angle right here between the x-axis and this line right here that we've got dividing the region into two equal sections is theta itself. And we said that I think you'd agree with me that the tangent of this mysterious theta is equal to y divided by x. Well, here's what's so exciting is that y divided by x is indeed your slope. Okay, so really, with respect to this question, we know that the tangent of alpha is equal to m, your slope. And if you were solving for alpha, we could just take the inverse tan of both sides, or arctan, however you like to say that or write that. So what I'm going to do is I'm just going to rewrite this setup right here, and I'm going to replace my alphas with the inverse tan of m. So I know that 1/2 the integral from 0 to inverse tan of m of r squared d theta is equal to, and instead of writing out, I am going to write out the second integral, I guess, just because this is kind of the way that I've committed to doing it. But you also could just have said that my first blue integral was equal to 1/2 of the answer I got from part B. It could be just strictly numerical on this side here. All right, r squared d theta. And that's really all we have to do for part C. We wrote an integral expression. We didn't have to solve it. That would eventually lead us to finding the value of m. All right, we're getting there. We're getting there. Our last part, D, says, hey, consider the function a of k, and that's going to be the area that's basically inside of S, but also inside of this new circle, k cosine of theta. And what you'll notice, when we have r equals cosine of theta, that's symmetric with respect to the x-axis. And then the value of k is just going to enlarge or dilate that circle. So let's see if we can get a glimpse of what this might look like. And again, we're using Desmos. And I know you guys don't have Desmos in the middle of an exam. Let me see if I can clean this up here. All right, so you'll see we've still got the original function there in red. And I've graphed this k cosine of theta function. And k is like a parameter, so to speak, and we're allowed to. So you'll see right now, if I left it at k equals 1, the area we're trying to find is of this little region right here. But as we let k grow a little bit, I'm going to go ahead and try to hit play on this k. Whoa, it got big in a hurry. In fact, I'll just shimmy it back here. So let's say k equals, okay, 7's reasonable. We can kind of play with that. So how would you just find the area of this region right in here? So what you would first do is you'd have to find this intersection point right here. And you do an integral from 0 to that intersection point. And in that time span, you'd be integrating the red petal, okay? And then what you do is you would set up a second integral whose bounds started at that intersection and continued until we got to pi over 2. Pi over 2 would take us back to the origin right there. And it would be the sum of those two integrals would be the area of this function there. I guess this they're describing it as a of k. But the question is, what is the area going to be as k approaches infinity? So this is actually going to be good news for us. What happens when k gets really, really, really big? Watch what happens as k gets really, really big here. So remember, like k is only at 10 right now, and we're getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. K is only at like 61-ish right now. Let's take it all the way to 100, and we're not even close to infinity right now. But basically, what we're doing here is we're going to find the area, basically everything inside the red curve that's in the first quadrant. So really all I need to do is, at first I was thinking I was going to have to do two separate integrals, and I was all worried about what that intersection point was and everything. All I've got to do, okay, is find the area of the red petal between 0 and pi over 2. Because essentially this intersection point that we were talking about earlier, that intersection is getting closer and closer to pi over 2. So we're just going to integrate from 0 to pi over 2. Let's see what that looks like back here in this page. So I'm thinking the limit as k approaches infinity of a of k is simply the area of that red petal from 0 to pi over 2. And again, we're going to use our calculator to evaluate this, and it turns out to be 3.324, which, how would you judge the reasonableness of that answer? Well, we almost found the area of the entire petal, but there was like that little sliver that dipped into the second quadrant. So compare this answer to your answer in part A. This answer right here is just a smidge smaller, so it seems very, very reasonable to me. But for me, everything came back to, could I visualize it? Probably got to use my calculator to see that graph and see what happens to this function as k gets bigger and bigger and bigger, which leads me to this as my upper bound. Ladies and gentlemen, I hope you feel a little bit better about polar functions. Half the battle with these is just not being intimidated by them. But I think we're ready to rock and roll. If you thought this was helpful, please hit subscribe below, share it with your friends, and we'll catch you later.